Good afternoon, everybody. Welcome to the day after July 4th, July 5th, and welcome to a wonderful afternoon at Chem 1105 with your host, me, Dr. White. Hi, everybody. I hope you all had a wonderful July 4th. I did. I was with my extended family yesterday. I guess in all sense, he's really my younger brother. By another mother, but we're that close. And coming home last night, I was able to time it right. And driving on the highway, I saw the fireworks from a number of cities as I was driving home. It was fun. All right, let's talk about some important things. And not that, that. All right, I'm going to go to student view. I'm going to go to assignments. And something I learned the other day from talking to a student, if you look at these, let's look at exploring let's do exploring density. Make sure you click on it like this to open it up so you can see all the instructions. If you don't click on the lab title in assignments, you'll miss some of the instructions. And what the student missed last week, or was Monday, didn't see this. And this is for lab 4. Notice I have how to determine and graph the slope in Microsoft SMS Excel. See the following video at 2425. And I have a link there. So the important things to remember when you're looking at an assignment, click on the title so you can see everything that I have written in the instructions. Notice the lab we did on Monday, because we didn't have class yesterday. It says, please do not, let's see if I can highlight, there we go. Please do not answer any lab report questions with the word classmate in it, but do the tables with your own cards. So again, when you're looking at the assignments, click on the title. That's a left click with your mouse. I got a nice one. And that's the mouse. And you'll see important information in the instructions. All right, that's one thing. Hold on. I see someone has a question. In terms of photographing, at least show for each activity one photograph. That's okay. They have you do a lot of them, but for each of the activities, pick at least one photograph. The rest of it you're going to put in tables and use to answer questions. So if you want to put more photographs, I'm not going to stop you. Go right ahead. Have fun. But for let me get for lab 7, this take a picture of the card arrangements for one you're supposed to do for each activity. You don't have to have 24 or whatever pictures in there. Does that help you, Julia? All right. As you notice the semester, wow, we're almost half done with the semester. We are half done. Wow, time flies when you're having fun with chemistry and a nice summer, even though we could use more rain. All right, that's one thing. The other thing I'd like to point out, here's the syllabus, and notice the week of the Thursday on the week of July 10th, next week, will be test number 2. Either today or tomorrow, I will finish chapter 5, part 1. And at that point, I will have covered all the material on test number 2. Now, let me just, here we are. So that means on Thursday the 13th, at least not Friday the 13th. Actually, Friday the 13th has been always a lucky day for me. But anyways, Thursday the 13th, I will be giving test number 2. And by Friday at the latest, maybe sometime tomorrow, I will post information about test number 2. But as you see on the syllabus, test number 2 will cover just chapter 4 and chapter 5, part 1. By the way, that's a lot of material. And test number 2 historically is the lowest average test of the semester, but not always. Last semester's class, it wasn't. I had a really good class last semester. I hope you people are all very good too. So don't forget to do the practice problems. All right, before I move on, any questions? All right, I promised today, so let's go through what I'm going to do. I'm going to go through chapter 4, practice problems. Then we'll continue with chapter 5, part 1. Don't forget tonight from 7 to 8, I have office hours. If you have questions, stop by. All right, let's look at chapter 4, practice problems. Even though I'm going through some of these, hopefully you are going through those too on your own first. All right, first question. Draw the Lewis structure for the following elements. What does that mean? Lewis structures involve valence electrons, the outermost electrons. Where do we find those? We find them in our friendly neighborhood periodic table. And the number on top, either Roman numeral, or as I found out a couple of years ago, they stopped teaching Roman numerals in grade school. I learned it there. The red numbers tell you valence electrons. And if we look at sodium, it has 1, so does lithium, so does hydrogen. Everything in the same column has the same number of valence electrons. Oxygen 6, nitrogen 5, carbon 4. Well, how do you draw a Lewis structure for an element? Well, you put 1 dot on each side of the element's chemical symbol for each valence electron before you double up. So if we look at sodium, had 1 valence electron, and one side has to have 1 dot. And I showed one way. There are 3 other sides, so there are 3 other ways you can do it. Now, carbon has 4 valence electrons, and you put 1 dot on a side before you double up. Let me show you something. Here's carbon. Here's the Lewis structure. This is wrong. Why? Because we have 2 on one side before each side has 1 dot or valence electrons. So you put 1 on each side before you double up. And let me show you in real time. Here's oxygen, has 6 valence electrons. And so I'm going to put 1, 2, 3, 4. 1 on each side, and now I'll double up. I don't know who started it, but organic chemists always do 1 on top, double and the other double on bottom, but you could easily, hold on, I gotta force my hand to do this because this is non-organic chem way. You could have just as easily done this. Any drawing with the chemical symbol, two sides have 2 dots, 2 sides have 1 dot. And if we look at iodine, iodine has 7 valence electrons. So you put 1 dot on each side, that's 4. Then you start doubling up. And you have 3 more to go. So 3 sides have 2 dots and 1 side has 1. Now I have the single dot on the right. It could have been on the top or bottom or left. And the other sides that didn't have the single dot would have 2 valence electrons. So that is how you draw Lewis structures for elements. Now, what ion will the following element form? Well, how do you do that? Well, let's do 2. Let's do magnesium. How do we do that? Well, you look at your friendly periodic table and say magnesium. Magnesium has 12 electrons and 12 protons. How do we know that? From the atomic number. And then you say, well, to be stable and happy, it wants the same number of electrons as the nearest noble gas based on numeric atomic number. And if we look at magnesium here, the nearest noble gases are neon at 10 and argon at 18, which is closer numerically to 12. And hopefully you pick 10, that's 2 away. Argon is at 18, 6 away. So that means magnesium would like to have 10 electrons. So how do you use that information to determine what ion magnesium will have? It has 12 electrons, 12 protons, but it wants to go to having 10 electrons and still has 12 protons. Each electron is a -1 charge. Each proton is a +1 charge. Do the math. -10 plus 12. I'll add those together and notice you get a +2. Well, we're not done yet. The question asks, what ion will magnesium form? And you show that by the chemical symbol and superscript. Now, there are 2 ways you can do it. The old way, which I like better, that's my personal preference, is +2. You could have also done the newer, I just had a M malfunction. Let's try that again. The new way, which I don't like, but is correct on my test, is 2+. Either way is correct on a test. Did I tell you I'm this close to the person grading the test? Me. So when I say either one is correct, I'm telling you the truth, because I'm doing the grading. All right, let's do one more. And let's try oxygen. What ion does oxygen form? Well, I've got the answer there, but how did I get it? Well, look at the periodic table. Oxygen, it's got 8 electrons, 8 protons. How did I know that? The atomic number tells me the number of protons and electrons. Now, what is the closest noble gas numerically based on atomic number? Well, you've got a couple of choices. Neon is 2 away. Helium, He, is 6 away. 8 minus 2, that's I got the 6. And argon is way, way far away, so we're not going to even bother with that. So you have a choice. 2 or 6, which is the lower number? And hopefully pick 2. And therefore, oxygen would like to have the same number of electrons as neon. So how do we deal with that information? We're trying to figure out what ion oxygen has. And from the periodic table, we know it has 8 electrons and 8 protons. Now it wants to go to have the same number of electrons as the nearest noble gas, neon, which has 10 electrons. The protons do not change. And therefore, each electron is a -1 charge, and there are 10 of them. Each proton, which we have 8, has a +1 charge. Do the multiplication, -1 times 10, minus 10, +1 times 8, +8. Add them together, and you get a -2. We're not done. The way to show the charge, chemical symbol, superscript to the right, the charge. Now you can write it the way I like to, or you can write it the way, the newer way. Either one would be correct. And we finished that. All right. What is the empirical formula for a molecule formed from the following ions? How do we do this? Well, you remember all molecules have a net charge. And let's do B, calcium +2, chloride -1. Oops, wrong color. Time for Dr. White to be subtle. So you should know this. All molecules have a net zero charge. So what does that mean for the problem? What is the empirical formula for a molecule with calcium +2 ions and chloride -1? Well, this is a +2 charge. This is a -1 charge, and it has to add up to 0. Oh, no, it doesn't. What do we do? Well, you can't change the charge. Students try and do that. This is an awful looking plus, but you can change how many. If this is a +2, how do we get this to -2 so it adds up to 0? You have 2 of them. And how do we show the formula? Well, this tells us when there's no number, it's the number 1 calcium and 2 chloride. And calcium chloride, the little white pellets you put on your sidewalk or driveway to melt the ice when it's real cold out, is calcium chloride, that molecule. Oh, this is fun. We got to do another one. Let's do D. Magnesium +2, nitrate -1. I have the answer there, but how did I get it? Let's look. So the question is, what is the empirical formula for a molecule with magnesium plus 2 ions and nitrate minus 1 ion? Well, all molecules, see, it says it on the screen, so it must be true. Oh, that was a bad joke. But anyways, all molecules have a net zero charge. Well, in that case, the empirical formula has to add up to 0. Well, if you look at this is a plus 2, but this is a minus 1. That doesn't add up to 0. You can't change the charge, but you can change how many. If this is a plus 2, how do I get this to minus 2? I put a 2 there. And now plus 2, 2 times minus 2 is minus 2, is up to 0. How do we show this? This tells us, because there's no number there, it's number 1, I have 1 magnesium. But now I have a polyatomic ion. When you have more than 1, in this case we need 2, use a bracket, write the ion. You don't have to show charges in an empirical formula, close bracket, and because we need 2 of them, we put the 2 there. Again, for a polyatomic ion, like NO3 minus nitrate, you use brackets to show more than 2. And that's how you do it. All right, draw the Lewis structure for the following. Well, how do we do that? We remember the octet rule. Except for hydrogen, which octet is 2, atoms share electrons for covalent bonds such that they have both their own and shared 8 valence electrons. So if we look at ammonia, NH3, how do we draw the Lewis structure for a molecule? And to draw the Lewis structure for ammonia, you need to know how many valence electrons hydrogen and nitrogen have. And how do we find that out? We look at our periodic table, hydrogen, 1 valence electron, the number on top, nitrogen, 5 valence electrons, that's the number on top. And since most of you don't know, V means 5 in Roman numeral, years ago I wrote the numbers on this because I found out they don't teach that in school. How bad. That's my own personal opinion. So we now know nitrogen has 5 valence electrons. Hydrogen has 1 valence electron, but don't forget there are 3 of them. Well, the only way to make this work is nitrogen will be in the center. And hydrogen, this hydrogen has 1 valence electron, and the nitrogen has 1 valence electron, and they share. Another hydrogen does the same thing, and the third one does the same thing. Now, let's look at this molecule. If I put a red circle around all of the electrons nitrogen has, both shared and non-bonding, that's the 2 on the top, how many are there? I'll let you count first. Yeah, you're right. 2, 4, 6, 8, 8. And that's an octet. Now let's look at hydrogen. If we look at each of the hydrogens, It has shared and non-bonding. There's no non-bonding. Each one has a pair of electrons. Remember, the octet for hydrogen is 2. The octet for hydrogen is 2. And each one does. So we're done. Let's do another one.
Dr. White, so on the test, we would write a total of 8?
Well, what you would write is what you see here. Okay.
Okay, so just that. You don't want us to like write a number down or anything.
Nope, nope. That
Okay.
I'm showing you. Let's go back. That's a very good question. What I'm showing here is the thought process you need to go through to answer this correctly. You'd have to know how many valence electrons each atom in that molecule has. And then you have to know how to put it together, like I just showed you. Does that help?
Yes, thank you.
You're welcome. And as you can tell, I promise what I do what I promise. And in my class, there's no such thing as a dumb question, ever. In my world, there's no such thing as a dumb question, ever. Thank you for your question. I'm sure other students would have the same. All right, let's look at nitrogen gas, N2. Right now, when you're inhaling, 80% of the gas you're inhaling is nitrogen gas. So we have to figure out, oops, wrong color. Unwhoops, right color. What is the Lewis structure for the molecule nitrogen gas N2? Well, we have 2 nitrogens, and each one has 5 valence electrons. Remember, look on top of the column of the periodic table, and we just did that, so I'm not going to do it again. And now, one way of doing it, and this part you do not have to write down, but it makes it easier to visualize what's going on. Here's the Lewis structure for each nitrogen. And if you look on each nitrogen, they each have 3 unpaired valence electrons, the single dots. And one nitrogen says to the other, hey, I have 3 unpaired valence electrons. You have 3 unpaired valence electrons. Let's share. And guess what? They do. So you have this nitrogen with 3 unpaired electrons that shares 3 unpaired electrons with this one, and we're done. How can we tell we're done? And this part you don't have to do, but I'm going to do it. If we look at this nitrogen, how many shared and unshared pairs of electrons do you see? 2, 4, 6, 8. It's an octet. And if we look at the other nitrogen, I'll do that in blue. How many in the blue circle, how many pairs of dots do you see? 4, which is 2, 4, 6, 8 dots. And that's an octet. So nitrogen gas, which I'll rewrite again without the circles, the Lewis structure would be that. And notice we have 3 pairs of electrons, and we call that a triple bond. So when you're inhaling nitrogen gas, you're inhaling a triple bond. Is that cool or what? Now you know I'm a chemist. All right, let's go to another molecule. How do you do this? let's look at I. I is sodium cyanide, NaCN. How do you draw the Lewis structure? Well, let's go back and look at the periodic table, because sodium has how many valence electrons? Look on top, 1. Carbon has how many valence electrons? Look on top, 4. And nitrogen, as we found in the last two problems, has 5 valence electrons. So now for sodium cyanide, sodium has 1 valence electron. Carbon, 4 valence electrons. And nitrogen, 5 valence electrons. Now, this is very important. Pay attention. Did I get your attention? Except for hydrogen. The alkali metals, which is in this class, lithium, sodium, and potassium, the first column, and the alkaline earth metals, for this class, magnesium and calcium, second column, under the 2, always form ionic bonds, which means in a molecule, those will always be cations. And we figured out for sodium, that forms a +1 cation, for magnesium and calcium, +2. So remember, when you're drawing the Lewis structure for a molecule, if you have lithium, sodium, or potassium, that's going to be a +1 cation. Magnesium and calcium are always +2. So what does this mean? Well, let's find out. Sodium will always be a +1. Now, carbon has 4 valence electrons. Nitrogen has 3. So the nitrogen says to the carbon, hey, I have 3 valence electrons. You have 3 valence electrons. Let's share. And they do. So it looks like this. 1, 2, 3. And then nitrogen, 1, 2, 3. The non-bonding pair of electrons are still there. And you have the sodium plus. Now, if we look at carbon, how many valence electrons do they have? Shared and unshared? 2, 4, 6, 7. That's not right. It's supposed to have an octet, 8. But wait, where did this valence electron go to form the plus charge? It goes here. Now, this polyatomic ion, it's called the cyanide ion, has a negative charge. And now we're done. Let me write it over again. So here is the correct answer for what is the Lewis structure for sodium cyanide. The sodium is always going to be a cation. It gives up one of its electrons to the cyanide anion. And here is the cyanide anion. This is a triple bond again, 3 pair of electrons. So between the carbon and nitrogen, there's a triple bond. Between the sodium cation and the cyanide anion, there's an ionic bond. So there are 2 different types of bonds, ionic and covalent. Remember, ionic is the transfer of 1 or more electrons from one atom or group of atoms to another atom or group of atoms. That's what the sodium did to the cyanide anion. Then a covalent bond is a sharing of one or more pair of electrons between two atoms, and that's what's between the carbon and nitrogen. And let's look at the last one. Name the three types of covalent bonds, and they are single bond, double bond, and triple bond. Now, what I don't have in this question that you should be able to do, name the three covalent bonds and how many pairs of electrons. Instant table. And the first one is a single bond. That's the first covalent bond, and that has one pair of electrons. Remember, a pair means two. And then the next one is a double bond, and that has two pair of electrons. And finally, the last type of covalent bond is a triple bond, and that has three pair of electrons. And I better be subtle again. Everybody get the message? Can't know this. And you should know that a single bond has one pair of electrons, double bond has two pair of electrons, and a triple bond has three pair of electrons. And that's the problem set for chapter 4. You should do this on your own without looking at the answers, because if you can answer all those problems correctly, you'll be in good shape for test number 2 coming up a week from tomorrow, Thursday, next week, Thursday, not this week. Now, one thing I neglected to mention, I just remember I did, bad Dr. White. If we go to announcements, you'll see this morning, actually at noon, I sent out put an announcement. I sent you an email that because I don't want test number 1 answers floating around YouTube for all of eternity, I made it a private video. And here's the link to that video. And you can see me going through test number 1 answers, which I did on Monday. And if you weren't there, you can watch it and see the answers. Now, if I look at the clock, this would be a good logical time. Let's take a 5-minute break. I will be back in 5 minutes. I can get up and stretch. See you in 5. Time to get going. All right, let's go back to chapter 5, part 1. And if you look on your screen, we talked about molar mass, otherwise known as what I call molecular weight, and that's the sum of all atomic weights of the atoms in a molecule. And remember, my special gift to you is for atomic weights on the periodic table on test 2, it will say underneath your name, first of all, please use proper significant figures for all calculated answers. And it will also say, please use 3 significant figures for all atomic weights. Therefore, nitrogen, which is 14.007, you should use 14.0. That's rounding that number off to 3 significant figures. Oxygen to 3 significant figures, 16.0. Chlorine at 35.453, I'll let you round that off to 3 significant figures, then I'll tell you what it is. It's your turn. Round off 35.453 to 3 significant figures. And it looks like everybody's done. So it's my turn. Keep the 3, keep the 5, keep the 4. That's my 3 significant figures. Next, the number 5 you use to round off. Is that 4 or less or 5 or greater? And it's 5 or greater because it's a 5. So I'll drop the 5, drop the 3, and increase the 0.4 by 1 to 0.5. So chlorine, the 3 significant figures, is 35.5. And this we did last Thursday, I think, but it's good review. So the question is, what's the molecular weight of hydrochloric acid, HCl? Well, how do you do that? The molecular weight is the sum of all atomic weights. Well, there's 1 hydrogen and 1 chlorine. And hydrogen to 3 significant figures has this atomic weight. Chlorine to 3 significant figures has this one. And you add them up and you get this number. But remember, when you add, you get the same number of significant figures to the right as the decimal, and all numbers to the right of the decimal are significant, as the number with the lowest significant figures to the right of the decimal. On the left, whatever you get, you don't change. So this has 2 significant figures. This has 1, which is the lower number. Hopefully you all pick 1. So now I'm going to round this off to 1 past the right of the decimal. keep the 5, use the 1 to round off. That's 4 or less, I'll drop it. And the correct molecular weight for hydrochloric acid using atomic weights of 3 significant figures is 36.5. And we did some practice time last week. Next, I talked about important concept, the relationship between mole and mass, meaning weight. And I'll never ask you to learn these definitions, but this is a better way of remembering it. 1 mole, and I really should have here, of an element equals the atomic mass or weight in grams. Now, this is from your book, and 1 mole of a compound like water, H2O, is the formula of mass, the molecular weight in grams, which is what we just figured. Now, let me remind you, you should be looking at important information, test number 2. And here I have my way of writing it, and you'll be given this. 1 mole of an element equals the atomic weight of that element in grams. 1 mole of an element equals the atomic weight of that element in grams. And we also have 1 mole of a compound equals the molecular weight of that compound in grams. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of a compound, which we just said, is the sum of all atomic weights. Now, in the past couple of years ago when I taught 1105, students would have to memorize this. And as I mentioned a couple of times, I've had a change of thought process. What should I test on a test in 1105? Your knowledge of chemistry or your knowledge of chemistry and how good your memory is? And I decided to do the first, which is why I'm giving you this. Will be at the last page of test number 2. You'll get a week from this Thursday. Well, let's use this to get some practice. So the question is, how many moles AU is gold of gold are 351 grams of AU gold? Well, how do we do this? Well, I think you know the routine. What are we being asked to find? Moles of gold. What, and that's AU, not AV. What are we given? 351 grams of gold. Well, the only thing we have to start with, and once we've done this, I no longer have to read this. Well, I won't. All right, this is the only number we have to start with. If I had a ratio, I could multiply a conversion ratio. What units do I want my answer to be in? Well, we figured that out right there. We want to go to moles of gold. And now it's time to use your good buddy, your good friend, unit analysis. Does everybody hear that whistle good over Zoom? Yes? Can you hear it?
You can't hear anything.
You don't hear this?
I mean, it just sounds very light.
Oh, that's sad. It sounds good. I'll have to work on that. Well, it's time to use your good buddy. Dun da da da. Did that come through? Your good friend. Dun da da da. Unit analysis. I'm sorry to hear that. This is a really nice, fun whistle. Do you hear this whistle when I use it?
Yeah, that one's better.
How about this whistle?
No.
Really? Wow. That's sad. All right. Well, I'm going to have to yell at Zoom. All right. Let's use our good buddy, our good friend, unit analysis. Whatever we're trying to get to, the units go on top of the ratio. Whatever we're trying to get rid of, the units go underneath. What I mean by get rid of is, do I want grams of gold in my answer in units? No. So that's why I put it underneath, because remember, anything divided by itself equals the number 1, which means it cancels out. So I'll write this in. Remember, G is grams. And where do I get a relationship between moles of an element and grams of an element? Well, in case you forgot, 1 mole of an element equals the atomic weight of that element. We have A equals B. You have 2 ratios, A over B and B over A. So if I know I have 1 mole of gold, I have to find the atomic weight of gold. How do I do that? I go to my friendly neighborhood periodic table, AU, 196.967. But remember, you're supposed to use all atomic weights, rounded off to 3 significant figures. And I'll give you 3 seconds to try on your own, round off 196.967 to 3 significant figures. I'll give you a couple more seconds while I have a drink of water. This is thirsty work. And the answer is keep the 1. Let's see. And one of your colleagues already got it right. Yay. Anyways, keep the 1, keep the 9, keep the 6. Use the 9 to round off. Is that 4 or less or 5 or higher? And does the and come through? Okay. And that's not 5 or higher. Drop the 9, 6, and 7. Increase that 6 by 1. So to 3 significant figures, the atomic weight of gold is 197. So what does that mean? I know for every 1 mole of gold, there's 197 grams of gold. 1 mole of an element equals its atomic weight. Well, now, before I pick up my calculator, grams of gold divided by grams of gold, we know this, therefore it cancels out. And we're left with moles of gold. Yay, that's what we want. And now I can pick up my calculator, turn it on, clear it. 351 divided by 197. Hit enter. And my calculator gives me this number. The reason I laugh, you'll see in a second or 2 or 3. And remember, on test 2, we'll say, please use all proper significant figures for all calculated answers. All non-zero numbers are significant, 3 significant figures. 197, 3 significant figures. The 1 is definition, so that's an exact number. Exact numbers do not play a role. Therefore, you get the same number of significant figures in your answer as the number that has the fewest significant figures. Well, in this case, they're both 3. So how do you round this off to 3? Keep the 1, keep the 7, keep the 8. That's my 3 significant figures. Use the 1 to round off. That's 4 or less. So I drop all this, and the correct answer is 1.78 moles of gold. Now, remember, practice this and the other ones I'll be doing, and they're under practice problems too. Let's do another one. NaOH is sodium hydroxide, and it's an important chemical the various industries throughout the world use to make things. I just wrote down sodium chloride. Where's my brain today? I guess it was sort of salty. Oh, that was a bad joke. Here we go. Well, what do? I'm going to have you do this stepwise with me. Help me out. Did I talk about Winky Dink in this class yet? I don't think I did. Let's do this, then I'll talk about Winky Dink. Who's Winky Dink? Well, you'll have to wait. All right, your turn. Let's do it stepwise. What are you being asked to find? What are you given? That's all I'm asking you to determine right now. What are you being asked to find? What are you given? Well, you people are getting the hang of this. Good. All right. We're trying to find how many grams, remember G means grams, of sodium hydroxide. What are we given? 7.112 times 10 to the 4th moles of sodium hydroxide. Now, there's only one thing we have to work with, so we will. This number. Now, if we had a magic ratio, it's not magic, it's chemistry, that can convert moles of sodium hydroxide to our answer, what units do we want our answer to be in? Your turn to figure that out. That's not what I want. And everybody's done. I was playing with the poll. And the answer is we figured that out. We want our answer to be grams of sodium hydroxide, NaOH. Now, your turn to figure out first what units go on top and bottom of that ratio. All right, it's time to use your good buddy, your good friend, unit analysis. And how do you do that? Whatever units you're trying to get to go on top of the ratio. Whatever goes underneath, we're trying to get rid of, goes underneath. And now I'll write that in. So we now have a ratio. We need to find numbers. What's the relationship between mole of a compound, sodium hydroxide, and weight, grams of a compound, sodium hydroxide? And how do we do that? We look at important information. Test number 2, in case you forgot this, 1 mole of a compound equals the molecular weight of that compound in grams. Uh-oh, we were not given the molecular weight of that compound. Well, you have to calculate that. That's why it's 8 points. It's a lot of extra work. And the molecular weight of a compound is the sum of all atomic weights. So in order to get the relationship 1 mole of compound equals the molecular weight of that compound, we first have to calculate the molecular weight of that compound, which is the sum of all atomic weights. And in our case, that's sodium hydroxide. So I know for every 1 mole of a compound, you have the molecular weight in grams of that compound. Well, the molecular weight of sodium hydroxide is the sum of all atomic weights. There's 1 sodium, 1 oxygen, 1 hydrogen. Each sodium has atomic weight to 3 significant figures of 23.0. Each oxygen has atomic weight to 3 significant figures, 16.0. Each hydrogen, there's only 1, has atomic weight to 3 significant figures of 1.0. Well, add this up, we get 40.01. Remember, when you add numbers, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. And all numbers, 0 or non-zero, when they're to the right of the decimal, are significant. So this has 1 significant figure to the right of decimal, this has 1, this has 2. When you do addition, you get the same number of significant figures to the right of the decimal as the number with the fewest. And what's the fewest? Hopefully I'll pick 1. So I keep the 0, use the 1 to round off, that's 4 or less. I'll drop it, and therefore the correct answer for the molecular weight of sodium hydroxide is 40.0, which I can put in here. Now, before I pick up my calculator, it's down there, I'm going to look and see what units, if I just do the math, I'll get for an answer. Notice moles of sodium hydroxide divided by moles of sodium hydroxide. Anything divided by itself equals the number 1, meaning it cancels out. I'm left with grams of sodium hydroxide. Yay, that's what I want. So now I can happily pick up my calculator, turn it on, clear it, put in 7.112 blue double key, key 4. That's how I get 10 to the 4th. And go back and look at the video or come to my office hours. You don't know how to do scientific notation on a calculator. And I'm going to multiply it times 40.0. And I can divide by 1, but I know that I don't have to because I know what anything. And my calculator gives me this number. But I'm not done, because you get the same number of significant figures in your answer as the number of significant figures, or the number of significant figures that the number you're multiplying, dividing, that has the fewest significant figures. And if we look at this, this has 4 significant figures. This has 3 significant figures. This 1 is an exact number, which plays no role. So I'm going to let you round off 2.8448 times 10 to the 6th to the right number for this answer, and then I'll do it. And everybody's done. So you get the same number of significant figures in your answer. And by the way, I put this 3 here. It really should have been up here, because this is 3 significant figures. That's 1 is exact number. Well, you got 4 significant figures, 3, which is the lower number. Hopefully you picked 3. So I'm going to round this off to 3 significant figures. Keep the 2, keep the 8, keep the 4. Use this 4 to round off. Is that 4 or less? Well, it's a 4, so you know it's 4 or less. And you drop that. And the correct answer for this problem is 2.84 times 10 to the 6 grams of sodium hydroxide. So if you need 7.112 times 10 to the 4th moles of sodium hydroxide, which is a solid at room temperature, you go to a balance and weigh out 2.84 times 10 to the 6, which is a lot of sodium hydroxide. And that's how you do it. Now, what I just did, and when I go stepwise and let you do stepwise, I'm stealing that from a program when I was about 5 or 6, yes, a long time ago, called Winky Dink. Now, it just so happens that just about everything except maybe my high school graduation is on YouTube. And if you look on your screen right now, you see that for a second, that little girl drawing on the TV screen where it says Winky Dink and you. And this was Winky Dink. And what you had to do, he went on adventures, and you had to draw. I'm trying to see if they show this. I can't find it. But anyways, you'd mail off, I don't know how much money it was, to that address. And what you would get is a piece of plastic and a grease pencil. And you put the plastic on your TV screen. Back then it was a TV tube screen. And during the cartoon adventure, Winky Dink, like I remember one. Why do I still remember it? Well, I do. Oh, kids, Winky Dink is stuck in the bottom of this hold of a ship. Help him get out. Draw a ladder in. And you see on the TV screen a dotted line where you should draw in the ladder. And you did. And he climbed up your ladder. And you'd clean off the screen again for the rest. Next time you got to help him out. And that's what I think of when I do stepwise, where you help me out. We're doing Winky Dink. Now, a Winky Dink story. Back when I was about 5 or 6, I lived in Chicago, and my best friend was Dickie Gale, who I haven't seen in about 35, 40 years. He moved out of state. But when we were little kids, he had Winky Dink too. And one time he forgot to put the screen plastic on the TV, and he's writing on the TV tube. Boy, did he catch it from his mother. Oh, that was not pretty. I heard about what happened after. He got punished big time. Bad. You don't write on the TV screen without the plastic. He forgot. But anyways, let's do another one of these. All right, question is 8 points. How many moles H2O, and I hope you all know by now that's water, are 7.8 times 10 squared grams of water? Let's do this stepwise. First of all, your turn. What are you being asked to find? What are you given? Again, your turn. What are you being asked to find? What are you given? And I'm going to assume everybody's done. So what are we being asked to find? Right here. How many moles of water? What are we given? Well, this number, 7.8 times 10 squared grams of water. So this is the only number we have to start with. If we had a ratio that can convert grams of water, what units do we want our answer in? Your turn. I see somebody already's got the right answer. Yay! So it's my turn. We're trying to find, because we already figured it out, moles of water. Now, what units go on top and bottom of that ratio? Not numbers, this units. All right. Well, how do you figure that out? It's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to, the units go on top of that ratio. Whatever we're trying to get rid of, the units go underneath. And I'm going to write that in now. So moles of water goes on top and grams of water goes underneath. And where do we find a relationship of moles of water, which is a compound, to grams of water, which is a compound? Well, in case you forgot, look at important information test number 2. By the way, this is located, this file, what you see on your screen is located in the lecture folder of Blackboard for 1105, and it's got the secret name, important information test number 2. And we'll see here 1 mole of a compound equals the molecular weight of that compound. And the molecular weight of that compound is the sum of all atomic weights. And water has 2 hydrogen and 1 oxygen. And remember on test number 2, 3, 4, and the final, it will say, please use all atomic numbers, weights, to 3 significant figures. Please use all atomic weights to 3 significant figures. Well, hydrogen to 3 significant figures, 1.01. Oxygen, 3 significant figures atomic weight, 16.0. And since we need the molecular weight, remember 1 mole of a compound is equals the molecular weight in grams. So we need the molecular weight of water, H2O. And there are 2 hydrogens and 1 oxygen. Each hydrogen has atomic weight, you just saw that, of 1.0 to 3 significant figures. Each oxygen, there are only 1, has atomic weight to 3 significant figures of 16.0. Do the math, 2 times 1.01 is 2.02, 1 times 16.0 is 16.0. Add them up, because the molecular weight is the sum of all atomic weights, we get 18.02. Now, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. All numbers to the right of the decimal are significant, including 0. So this has 2 significant figures. This has 1. Your addition answer should have the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. In this case, that number is 1. Keep the 0, use the 2 to round off, that's 4 or less. So to 3 significant, or the proper atomic, that proper molecular weight of water using significant figures for each significant figures for the atomic weights is 18.0, which I can put in here. We check grams of water divided by grams of water. Anything divided by itself cancels out because it's equal to number 1. And we're left with moles of water. If we look up here, that's what we're trying to find. Yay. So now I can happily pick up my calculator, turn it on, clear it. I have 7.8 blue double E key 2 divided by 18.0. And my calculator gives me this number. You'll see why I laugh. And remember, your answer should have the same number of significant figures as the number that has the lowest significant figures in the number you're multiplying, dividing. This is, I'll help you out, but you should do this on your own. Everybody hit pause button and figure out how many significant figures everything you're multiplying, dividing by. Now you can turn it back on. And this is 2 significant figures. All non-zero numbers are significant. The 1 is an exact number, not used in determining significant. And 18.0 is 3 significant figures. And your answer should have the same number of significant figures as the number you're multiplying, dividing. That's the lowest. That's 2. So how do we convert this into significant figures? Keep the 4, keep the 3, use the next number, which is a 3, to round off. Is that 4 or less? Yes. So that means I drop this and all these 2. And the correct answer for this problem would be 4.3 times 10 to the first moles of water. So if we needed, and you could have also written this like this. For this number, I would accept this numeric value. So if we needed 7.8 times 2 grams of water, how many moles would that be? 43 moles of water. And I can't stress enough, you should do the practice problems on these type of mole conversions. We'll need it later on, and it'll be on test 2, and students have difficulty with that. Monday and today, I think I've done about 4 of these problems. Oh, wait, let me get that fixed. It's fixed now. And I'll do some more tomorrow, but it's time to move on. So we've determined the mass in moles for different things. We've done, if you look at this chart, we've converted moles to elements to grams, and we didn't do moles of a compound to grams, but we converted of a element. Well, we did do, I'm sorry, we did do moles of a compound to grams, and we did do grams of a compound to moles. And you should know how to do these. And we did examples on the board, our whiteboard. So let's move on. Now, switches off for this, but it's an important concept. That's called conservation of mass. And the law of conservation of mass in any chemical reaction, the total amount of matter in the reactants is equal to the total amount. This got attacked by the dreaded T virus. It stole the T right, or now it's back. The total amount of matter in the products. So when you're doing a chemical reaction, A plus B makes C plus D, the total amount of matter A and B has to equal the total amount of matter in C and D. And that's called the law of conservation of mass, or just conservation of mass. I'll never ask on a test what it is, but I'll expect you to know how to use it. Well, how does that play a role? What I'm about to tell you is probably one of the most important and powerful things I know in all of chemistry. I'll say that again. What I'm about to talk about is probably one of the most important and powerful things in all of chemistry for me, and probably for a lot of other chemists. Calculating moles using mole factors in calculations. What does that mean? Here's what it means. In your book, it says the coefficients in a balanced equation, chemical equation, give the numerical relationship among formula units consumed, used up, or produced in a chemical reaction. A better way of saying that, the way I like to say it, the coefficients in an equation give the fixed molar ratios between substances consumed or produced in a chemical reaction. And what I should have also had here is balance. The coefficients in a balanced chemical equation give fixed molar ratios between substances consumed or produced in a chemical reaction. Practice time. What does this mean? What does this mean? The coefficients in a balanced chemical equation give fixed molar ratios between substances consumed or produced in a chemical reaction. Well, let's look at a balanced chemical equation. And notice you have 4 hydrogen, 2 oxygen, make 2 water, which has 4 hydrogen, 2 oxygen. So this is balanced chemical equation. But what do those coefficients now mean? And again, this is one of the most powerful things I know in all of chemistry. What it now means is you react 2 moles hydrogen gas. When there's no coefficient, that's the number 1. You react 1 mole of oxygen gas. And what do you make? You make, look at the coefficient, 2 moles of water. So the coefficients, the number in front of a balanced chemical equation of the formula, either the elements or the formulas, chemical formulas, give you molar ratios. And that tells me 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. Where do we get those numbers? From the coefficient. 2 moles of hydrogen. When there's no coefficient, it's the number 1. 1 mole of oxygen makes 2 moles of water. Let's do another one. Let's take a Here I have another balanced chemical equation. 2 sodium, 2 sodium, 2 chlorine, 2 chlorine. What does this now tell us? It tells us there are 2 moles of sodium. The coefficient gives molar relationships. When there's no number, it's the number 1. 1 mole of chlorine gas, and they make 2 moles of sodium chloride. Again, the coefficients, the number in front of a balanced chemical equation gives you molar relationships. When there's no number, it's the number 1 implied. So again, let's look at this and what does it mean? All right, question is 5 points, and you will be given this balanced chemical equation, this problem. You need it to solve it. How many moles of water, H2O, are made or produced when you react 5.16 moles of oxygen gas with an excess of, I forgot the F here. Sorry about that. Now, what are we being asked to find? And the question is, how many moles of water? So we're given moles of water. That's what we're trying to find. We're given 5.16 moles of oxygen. Now, whenever you see an excess of another chemical, know what that means? You can forget about it because that tells you you've got all the hydrogen in the world that anything that hydrogen can react with will. So when you see excess of something, that means ignore me, and I will. So if we look at this, what do we have to start with? Oops. we have moles of O2. What units do we want our answer to be in? Moles of water. So if I have a relationship or conversion factor, something divided by something else, how do I convert moles of O2 to moles of water? I use my good friend, my good buddy, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And now I'll write that in. And where do I find a relationship for this problem between moles of oxygen and moles of water? We look at the balanced chemical equation. Look at the coefficients. This tells me 2 moles of hydrogen gas react when there's no coefficient. It's the number 1 mole of oxygen gas to make 2 moles of water. So if I look here, I see for every 1 mole of oxygen gas, which I get here, makes 2 moles of water. Again, look at the balanced chemical equation. The relationship, the coefficients gives you molar relationships. Here, 2 moles of hydrogen. Now, because we see excess hydrogen, we don't need that, but I still wrote it down. But 1 mole of oxygen makes 2 moles of water. We get that because the coefficients of the balanced chemical equation give us that ratio. When there's no number, it's the number 1. Now, the coefficients are exact numbers. Again, the coefficients are always exact numbers, which play no role in so many significant figures. Now, before I pick up my calculator, notice we have moles of oxygen divided by moles of oxygen. And this cancels out because anything divided by itself equals number 1, which means it cancels out. And I'm left with moles of water. So now I can pick up my calculator, turn it on, clear it, 5.16 times 2. You don't have to divide by 1. You know what that's going to get. And my calculator gives me this number. Now, when you multiply and divide, you get the same number of significant figures in your answer as the number with the fewest significant figures. And here, this has 3 significant figures. Ooh, we got an exact number here, exact number there. They don't play a role in there. What's the lowest number of significant figures? Well, there's only one number we use with significant figures. This calculation is 3. So now we have to round off our answer to 3 significant figures because you get the same number of significant figures in your answer as the number that has the fewest significant figures. Somebody already did it right. Yay. But anyways, to get 3 significant figures, keep the 1, keep the 0, keep the 3. That's my 3 significant figures. The next number to round off is at 4 or less or 5 or higher. 4 or less. I'm going to drop that. And my answer is now, since this number is small, you could have also written this. And I would accept on a test. And that's how you do it. Now, what was the key to this problem? The key was that the coefficients, the number in front of a balanced chemical equation gives you molar relationships. And for this one, 2 hydrogen, 1 oxygen make 2 water, and that's 2 moles of hydrogen make 1 mole of oxygen with that. Let me start that again. 2 moles of hydrogen reacted with 1 mole of oxygen to make 2 moles of water. And since we're trying to find a relationship between moles of water, moles of oxygen, it's right here. 1 mole of oxygen, that's where I got the 1 from, makes 2 moles of water. That's where I got the 2 from here. And that's how you do it. If I look at the clock, oh no, we're out of time. Time flies when you're having fun with chemistry and moles and Dr. White. All right. Don't forget, tonight I have my office hour from 7 to 8. Don't forget, do the practice problems. Do the one so far in chapter 5, part 1 that I've done already in lecture, because this test number 2 will have that all on there, and students have problems with that if they don't practice. I don't want to see you have problems. I want to see you get a good score on test number 2, which is coming up a week from this Thursday, which will be, what day is that? And I'll put out an announcement by Friday of this week, Friday late morning, about this, but don't forget, July 13th, I will be giving test number 2 online, just like I did test number 1. And with that, I'll say, gang gesund, that means go in health in Yiddish. My grandmother used to always say that to us when we left after visiting her. Great lady, Grandma Greenman, Bessie Greenman. What a great lady she was. Probably one of the finest people I've ever met in my life. But remember, gang gesund, go in health. Goodbye.